Today, we are diving into the invisible architecture behind pretty much every piece of complex software you use. It's called system modeling. And honestly, the best way to think about it is as the master blueprint that turns a really cool idea into a functional, reliable app. I mean, have you ever stopped to think about that? How do huge teams, sometimes with hundreds of developers and millions of lines of code, build something massive without the whole project just, collapsing into absolute chaos? How does everyone stay on the same page?
Well, the answer is actually pretty simple, and it's the exact same way you'd build a skyscraper. You start with a blueprint, a really detailed plan that everyone on the team can understand, follow, and always refer back to.
And in the software world, that blueprint is called a system model. So let's break this down. System modeling is just the process of creating these abstract models. The key thing to get here is that it's not just one model. A complete system blueprint is made up of several different models, and each one gives you a different perspective. Kind of like how an architect needs the floor plans, the electrical plans, and the plumbing plans to really capture the whole design.
So why go through all this trouble? Well, because these models are incredible communication tools. Yeah, they help the dev team really understand what they're building, but just as important, they're used to talk to customers and stakeholders, the people who aren't developers. They can make it crystal clear how an old system works before you try to replace it, or perfectly spell out the requirements for a brand new one.
All right, let's break this down into a few parts. First up, mapping the environment. Before you can even think about designing the building, you have to understand the neighborhood it's going to live in.
And that's exactly where system modeling starts too. The very first view you need is the external perspective. This isn't about what's inside the software yet. It's all about what's outside it, how it's going to connect and relate to the world around it. The tool for this is called a context model. Its one and only job is to draw that critical line in the sand, the system boundary. It shows us what other systems we need to talk to and what's totally outside of our control. And trust me, getting this boundary right from the start is one of the most important decisions in the whole process. So once we know where our system fits in the world, the next logical step is to figure out how it's going to talk to everything else. This is the interaction perspective, where we map out all the conversations between our system and the outside world. And this slide makes that idea really concrete with what's called a use case. We're looking at a hypothetical medical system called MentCare. The task is simple: transfer data. Notice how it defines the actors involved, in this case, a person and another computer system. It shows the stimulus that kicks the whole thing off and the expected response that tells us it worked. You basically map out every single interaction just like this. Okay, let's move on to part 2. We've got the outside figured out, so now it's time to design the interior. We're talking about the floor plans and the wiring of our software. And this slide just illustrates the two ways we model the inside of a system perfectly. On one side, you've got structural models. Think of these as the floor plan. They show the static parts, the components, the rooms, and how they're all connected. On the other side, you've got behavioral models. These are more like the wiring. They're all about the dynamic stuff, showing how the system acts and responds when something happens, like when you flip a switch. So let's start with that floor plan, the structural perspective. This is all about the static organization of the software's components. The most common way to do this is with a class diagram. Now, in the programming world, a class is just a template for a thing. To stick with our analogy, a class diagram doesn't show you every single room. It defines the types of rooms we can have. It says, okay, in this building, we're going to have kitchens, bedrooms, and bathrooms, and it shows how they're related to each other, like how a bedroom is often connected to a bathroom. All right, now for the wiring. The behavioral perspective isn't about what the system is, it's about what it does. It's all about modeling the dynamic behavior of the system while it's running, showing how it reacts to different things. This can feel a little abstract, so let's ground it in something super simple that everybody gets: a microwave oven. So the basic idea of behavioral modeling is that a system can only be in a limited number of states at any given time. For our microwave, these states are things like waiting, full power, or operation. At any one moment, the microwave can only be in one of these states. And here's the crucial part. Behavior is just the act of moving between these states. So it works like this. The microwave is in the enabled state, ready to go. Then an event happens, a stimulus, like you pressing the start button. That event causes a transition, and the microwave moves to a new state, operation. And that's behavioral modeling in a nutshell. States, events, and transitions. Simple as that.
And that brings us to our last section, where we get to look at the future of all this. What if we could take these models one giant step further, from just being a plan to something way more powerful?
This leads to a pretty wild idea. What if the blueprint wasn't just a guide for human programmers? What if the model itself could actually generate the code and build the software automatically? This is the core idea behind something called model-driven engineering, or MDE. And this quote just sums it up perfectly. With MDE, the main goal isn't to write program code anymore. The goal is to create an amazingly detailed model. The code itself then just becomes a secondary thing, generated automatically from that model.
Now, this sounds incredible, right? The potential is huge. It lets engineers work at a much higher, more conceptual level. And if you need to move your software to a new device, you don't rewrite it. You just regenerate the code for that new target. But the reality is a little more complex. The kinds of abstractions that are great for design might not be the most efficient when it comes to actually running the code. And the cost of building those code generators, the translators, can sometimes be even more expensive than just writing the code by hand.
So let's do a quick recap of the blueprint we just walked through. First, system modeling is the essential plan for managing the complexity of software. Second, a complete model looks at the system from 4 angles: its external context, its user interactions, its internal structure, and its dynamic behavior. And finally, the future of this whole field, model-driven engineering, wants these blueprints to actually build the software themselves.
And that leaves us with one final thought to chew on. If a model can automatically build the system, what does that ultimately mean for the role of the software developer, the builder? It's a question that suggests the future of how we create software might look very, very different from how it looks today. Thanks for tuning in.